a regular expression, and one example where I have explained how that regular expression is generated. Now we'll see some more examples on the regular expressions. So suppose my L2 is a string W such that W is a binary string which ends with 1 but does not contain the string only 0 0. Previous case we have seen that it should not contain 0 0 as well as 1 1. So now it should not contain 0 0 but it ends with 1. So now suppose the example here is, if you see the string, it does not contain 0 0 as well as it ends with 1. So it means that it belongs to L. And suppose this is a string, it uh, does not ends with 1, that is also not true, as well as it is containing 0 0. So both the conditions are failed. If any one condition fails also, that string does not belongs to the language L. And suppose here the goal is to build the regular expression for L2, then the required regular expression for L will be equal to, it has to end with it should not contain 0 0. It means that it can be 1 plus 0 1 whole star. So this star, it generates the string epsilon 1 1 1, any number of ones, and 0 1 0 1 1 1 0 1 0 1 0 1 0 1, so any such combinations, and 0 1 with the concatenation with any number of ones. All such strings will be generated from here. And since it has to end with 1 or 0 1, it means that the minimum string length will be equal to 1. So it means that it has to be ended with the 1 or 0 1. So that is the meaning of this last. So this could be generating empty string, and it has to be concatenated with 1 or 0 1. So this is the regular expression for the required language. So let us see one more example. That is, W is a binary string which ends with 0 1. It means that the minimum string is 0 1. So the string is 0 1, and here it is just saying it has to end with 0 1. So that any string any remaining string I can generate by using 1 plus 0 whole star. So I can use any of these combinations of clean closure with the union. So I can generate epsilon 0 1 0 1, all such things I can generate. And since it says that it has to end with the 0 1, so 0 1 will be at the end. So these are some more examples which represents the regular expression as well as the language representation or a regular set. So suppose the regular expression is 0 plus 1 0 whole star. It means that my language contains 0 or 0 1 1 0, that is 0 1 0 1 1 0 1 0 0 0 1 0 0 0 0, any such things. So here it is infinite because of 1 0 whole star. So if I use this 0 star as a 0 raised to 0 raised to 0, I'll get 1. If I use 0 raised to 1, I'll get 1 0. If I use 1 0 raised to 2, so I'll get 1 0 0. So such is the set of all strings I can generate. Suppose the next is 0 star 1 0 star. So both star star I can put first at 0. So I'll be getting the string 1. Next I can put this is 0 and this is 1. So I'll be getting 1 0. If I use this is 1 and this is 0, I'll be getting 0 1. So I'll be getting 0 1 1 0. Likewise, if I apply this star with combinations of any combination values of 0 1 1, it could be, this could be 0 with any string, 1 with any number. Likewise, I'll be getting such different strings. So likewise, 0 plus epsilon plus into 1 plus epsilon. So which means I can get only the string epsilon 0 1 0 1. So this a plus b whole star, it can generate all set of strings of any length including the null string, because this star could be empty. So at that time it could be empty, a, b, a, all the strings of a and b. Next is a plus b whole star ABB. It means any strings ending with ABB. This is all strings of ones only, which are of even length. Next is even number of A's followed by odd number of B's. Next is strings of A's and B's of even length by concatenation of the strings AA, AB, BA and BB. So which includes all strings of even length. So it contains epsilon also, actually it has to be written epsilon, EA, AB, all strings of even length. So these are some of the examples. Let us see what is called as Kleens theorem, part 1. So you have two parts. First part we'll see today. So now this Kleens theorem part 1 says that for any regular expression R which represents the language L of R, there is a finite automata which represents the same language. And I said that finite automata could be epsilon NFA, NFA or a DFA. So now this Kleens theorem part 1, it can be represented like a regular expression to epsilon NFA conversion. Now suppose your epsilon NFA1 and epsilon NFA2 are the automata for the regular expression R1 and R2. So it means that for epsilon NFA I have R1, for epsilon NFA R2. Then what is the regular expression for R1 plus R2 represents which machine? Or R1 and to R2 concatenation, what does it represent? And closure for R1, what does it represent? That is R1 star. So now with the epsilon transition, the construction for union, concatenation and closure is represented here. So suppose you have one machine for R1, another machine for R2, then you create a start state with epsilon transition to the start states of epsilon NFA and epsilon NFA2. That means from the epsilon NFA1 and NFA2, you create one new start state and add an epsilon transition to the start state of this epsilon NFA1 and 2 and create a new final state with epsilon transition from the final states of epsilon NFA1 and epsilon NFA2. So that is nothing but, so suppose you have this S and T are the two regular expression, then S plus T will be the final regular expression. So here this was the start state and this was the final state of S, and this is the start state and this is the final state of T. Now the union will be obtained by taking a new start state and adding an epsilon transition to the start state of S and T and changing these final states of S and T to non-final state and adding a new final state and adding a new epsilon transitions from these previous final states to the new final state. This we call it as a union machine for the regular expression S plus T. So likewise for the concatenation, suppose S is a regular expression for this machine and T is a regular expression. Now suppose this is the start state, this is the final state, this is the start state, this is the final state, and make this start state of S as the start state of the S and T, S followed by T, and make this final state of S as a non-final state and add an epsilon transition to the start state of T and consider the final state of T as the final state of the concatenated machine. So this will be your concatenated machine for S into T. Now for S star. So suppose this is your machine which has, this is a start state, this is a final state. What we do is you create one new start state and add an epsilon transition to the start state of S and make this as a non-final state and add a new final state, and from the previous final state add an epsilon transition. So these are the first step. Then add a new transition from the final state of S to the start state of previous start state and add a epsilon transition from the new start state to the new final state, because S star should contain all the strings which are repeatedly obtained by repeating the strings of S. So I need to apply this any number of times and I have to apply accept the empty string also. So I have to add one final transition. So let us see one example how to convert regular expression to epsilon NFA. Suppose my regular expression is AB plus A whole star. So now how do I write the machine for this regular expression? Suppose that for the A, I have this is a machine. For B, I have the machine. This is the start state, this is the final state, and A is the transition, B is the transition. Now if it is a AB, so this A has to be followed by B. So add one new transition and make one which connects from the final state of this to the start state of this. So this is your AB. Now I will take the next step, that is AB plus A. This is my AB, for which whenever it is plus it is a parallel. So AB or A, or is nothing but plus, which is another path. Next is whole star. So this you have, and make one new start state and add an epsilon transition, and from this add an epsilon transition to the new final state and add one epsilon back to the machine of the previous stage. And this, because it has to accept the epsilon empty string, so from the start state you add a epsilon transition to the final state. This is how we can construct the machine for the regular expression, epsilon in FA for the regular expression. So likewise, given any regular expression, I should be able to obtain the epsilon in FA. This is what your Kleens theorem part 1 tells you. Thank you. We'll stop here.